Now that we know what average rate of change is, we can move on to the really exciting thing, which is instantaneous rate of change. When you're going on a trip in your car and you look down at the speedometer and it says 60 miles an hour or 100 kilometers an hour, is that giving you your average rate of change since the start of the trip? No, it's claiming to give you what your rate of change is, what your velocity is at that exact moment. Somehow it is finding out what your rate of change is right now, instantaneously. And that's what we can use calculus to figure out. So here's an example. So our function f of t equals t squared meters is a hummingbird's height above ground at time t seconds. You know, a hummingbird can just sort of fly up and down, straight up and down. So we're going to imagine that that's what the bird is doing. And we'd like to figure out what its instantaneous velocity is. And velocity is the rate of change of the height. There's a distinction between velocity and speed, which we'll talk about later. Velocity has direction. So in this case, we would know whether the hummingbird was going up or going down, whereas speed does not have any direction. Speed is the absolute value of velocity. So we'd like to try to figure out how fast this hummingbird is traveling, what is its instantaneous velocity up and down, exactly at time t equals 1. Now, we don't yet have enough calculus to answer this question straight off, but we're going to build on what we already know about average rate of change. So if we take a first attempt, we could try to compute its average rate of change, its average velocity, on a very tiny interval from time 1 to, say, time 1.1. So using just what we did before. So we would take f of 1.1 minus f of 1 over 1.1 minus 1. The top of the fraction represents the change in the height in meters, and the bottom represents the change in time. So f of 1.1, we plug that into our function t squared. We should get 1.21 meters. F of 1 is 1. And on the bottom, we have 0.1 seconds. So during this 1/10 of a second, the hummingbird went up 0.21 meters. So 0.21 over 2.1 is 2.1. And we should check to make sure the units are reasonable, in case we didn't get the fraction upside down or something like that. The units on this are meters. The units on this are seconds. So meters per second, which is exactly what you would expect for a velocity. So we could make a guess. We could say, oh, it's probably about 2.1. Now, this was looking from time 1 forward to time 1.1. We could just as well have looked backwards 1/10 of a second. There's no reason to suppose that looking 1/10 of a second forward is better than looking 1/10 of a second backwards. So we could do exactly the same calculation here. F of 1 minus f of 0.9 over 1 minus 0.9. F of 1 is still 1. F of 0.9, when we square 0.9, we get 0.81 over 0.1. So that means that during this 1/10 of a second, the hummingbird rose 0.19 meters, and 1.9 over 0.1, or sorry, 0.19 over 0.1 is 1.9 meters per second. So now we have two estimates for how fast the bird was traveling at time 1. 2.1 meters per second, 1.9 meters per second. So now we've looked at this as a formula, as a number, and as promised before, we'll look at it graphically. So these are secant lines. So this 2.1 is the slope of the secant line that connects these 2 points. And this 1.9, this graph is intentionally not drawn to scale so that we can see the distinction, is the slope of this secant line. So this slope here is 2.1, and this slope down here is 1.9. Now, if we want to get a better estimate, what would we need to do? We would want to use smaller intervals. So instead of 1/10 of a second, maybe 1/100th of a second. If that's not good enough, 1/1000th of a second. Now, is any of those actually going to give us the exact answer? And the answer to that question is no. We'll need to use some calculus to get the exact answer. And to get the exact answer, we'll want to think about what happens as we squeeze these intervals closer and closer and closer together. So as these secant lines get shorter and shorter and shorter. So if you hold this point at 1 and squeeze this other point closer and closer and closer to 1, from either from the left side or the right side, and I think you can guess where this is going. If we're talking about coming from the left side or the right side, we must be talking about computing a limit, as we did in week 2. So now we have an applet for you to explore what happens to this particular function. And you can change the function as well and play around with other functions. You've got all sorts of things you can do with this applet. See if you can come up with a guess at what you think the instantaneous velocity will be exactly at time 1 by trying to take the limit of these secant lines. And the applet will show you the numbers and it will show you the graphs. So please go play around with that applet and then we'll come back.